Okay, so yeah, good evening everyone. So this is Diljit Datta here. I am a research scholar in Indian Institute of Science. So we'll be starting today's session, that is today's problem solving session on the course Hydraulic Engineering. And yeah, so let's get started. I'm turning off my video now for so that you can hear my voice properly and there is no disturbance in video. So yeah, let us get started. So in this session we'll be covering mainly non-uniform flow in open channels. So inside this topic there will be two main topics. One is the uh, determination of mean velocity of flow in open channels, and secondly we will be seeing two types of non-uniform flows, that is gradually varied flow and rapidly varied flow. And inside rapidly varied flow there are two types of rapidly varied flow. One is hydraulic jump, another is surges. So we'll see through the topics one by one, and before going to gradually varied flow, let us see how we can measure the mean velocity of flow in open channels. So what are the instruments that are used? There are two main instruments that are used for measuring mean velocity in open channels, that is in rivers or streams. So first open channel first instrument is a pitot tube. I have shown the mechanism of a pitot tube in I think week 2 or week 3 lecture, how a pitot tube can be placed in a channel or a pipe, and then based on the height of water in the pitot tube we can get the velocity of the flow. The second device, measuring device for velocity of flow, is called a current meter. So this is most widely used instrument for measuring the velocity of flow. And a current meter is mainly of two types. One is the cup type and one is a screw type. So you can see in the figure that is shown here, there it shows a current meter. So this is a vertical current meter, vertical section of a current meter. So it is dipped inside the water, that is in a river or a stream, and you can see suppose if water, this is the water level, if we are seeing this is the water level and water is moving in this direction. So in that case these are the cups in the current meter. So as the water will be flowing, it will be rotating the cups. It will put some force on the cup, and these cups will be rotating. These cups will be rotating, and based on the revolution, that is RPM, revolution per minute of the cup, we can get the velocity of the flow. So this is one type of current meter, that is the cup type, and the second type is the screw type. This is shown in figure B. In this thing, in the screw type current meter, you can see screw is fitted instead of a cup, and it will have 2 or 3 wings. So as the water will be putting force on the screw will be rotating, and based on the revolution per minute RPM, and based on the RPM of the screw, we can get the velocity of the flow in the river or the stream. So this is the main working principle of a current meter, that is, a wheel is rotated by the flowing water. The number of revolutions of the wheel per unit time is proportional to the velocity of the water. So in order to get the velocity, the current meter is first calibrated. So it is placed in a lab flume. It is placed in that, and for different velocities of the flume, the current meter is then calibrated so that we can get the velocity of the flow in river accurately. So this is one type, is current meter, and the third measuring object of a measuring device is called the float. So these floats are mainly used in coastal areas or estuaries. So in that case, it is difficult to uh, measure the velocity with a current meter, since the flow directions are mostly bidirectional. That is, it is in river the flow velocity is mostly unidirectional, that is, it is only in one direction, that is along the length. But in case of coastal areas, the flow velocities can be in both x and y directions. So in that case, the float is used generally for measuring the surface velocity. So what is a float? So this is the figure of a float. So it is a something hollow metal sphere that is placed on the surface of the water, and it is then connected to a very heavy object at the bottom. So when the water will be moving, the float will be moving along with the water. So based on the distance covered by the float in the water and getting the time to move the distance, we can get the velocity, that is distance per unit time. So in whatever direction we want, suppose if we consider this as x and along the paper is this is y. So if based on the whatever direction we want, if we want the velocity in x, so we'll see what distance it has covered in x direction, and based on the time taken to cover that distance, we can get the velocity in x direction. And similarly, if the float is moving in y direction, the distance covered in y per unit time will give the velocity in y direction. So this is a single float. So there is one more thing called a double float method. It is a more accurate method for measuring flow. So what is the principle of a double float method? So this is a double float that is shown here. So what it consists of a spherical float to which a hollow metal sphere heavier than the water is suspended from the float by a cord of known length. So a hollow metal sphere is connected to the float and by a wire, and we know the length of the wire. So the depth of the lower float, which is completely submerged, may be regulated by the length of the cord. The velocity is obtained by noting the time taken by the float to traverse a known distance. Similarly, the single float. However, this float gives a velocity equal to mean between the velocity of the surface and the velocity of the layer traversed by the lower float. The thing is that when you are using the surface float, it will give only the velocity at the surface, but the mean velocity is not generally the velocity of the surface, so it will be somewhere in between, that is at some distance from the top. So this will give the mean velocity. So if we use a double float, so we have two metal spheres to one float and connect to a hollow metal sphere. So based on the distance covered by both the metal sphere and the float, we can get the mean velocity by taking the average of the distance, average of the velocities covered by the float and the metal sphere. So this will give the mean velocity of the flow. This is a better method for if we want to get the mean velocity of flow. And similarly, there is also one type of float called the rod float, which is shown in figure as in the second figure. So a rod is fitted to some weight at bottom, and the length of the rod should be reaches the bottom of the strip. So based on the distance covered by the rod along the x or the y direction, we can get the velocity in both x and y direction. Okay, so this was some basic insight into the measuring devices that are used for getting the velocity of flows. Now let us go to the main topics of today, that is gradually varied non-uniform flow. So non-uniform flow can be of two types. One is gradually varied flow, and the secondly it can be rapidly varied flow. So gradually varied flow is a steady non-uniform flow. So it is gradually and rapidly varied flow is a unsteady non-uniform flow. So first we will go through gradually varied flow. So we will see through what is the dynamic equation of the gradually varied flow, and there are some assumptions that are there in gradually varied flow. The first assumption is that the energy slope is evaluated by Manning's or Chassis formula. So we'll be only using these two formulas for getting the energy slope. And the bottom slope is small. It is not that steep, not extremely steep. And thirdly, we will be considering a prismatic channel, and that prismatic means it is in the shape of a rectangle. And thirdly, we will have consider hydrostatic pressure distribution. The pressure distribution along the depth of the channel is hydrostatic. So based on these assumptions, we get the dynamic equation of a gradually varied flow. If we take the total height as height of total energy line as h, so h equals to z plus y plus v square by 2g. Z is the height of the slope from the datum, y is the depth of water, and v square by 2g is the head due to kinetic energy. So the total energy, then we say that if we take the difference of if we differentiate both left hand side and right hand side of this equation, we will get dh by dx equal d by dx q square by 2g square dy by dx plus dz by dx. So dh by dx will give the friction slope, that is slope of the total energy line. Dz by dx will give the slope of the bed, that is s naught. Dy by dx is the slope of the water. We want to evaluate that. And say thirdly, the four terms, if we simplify that, you can take q square by ga cube g 2g outside, and if we differentiate 1 by a square, then we will get this term. So after rearranging the terms, we will get the final equation, dynamic equation of a gradually varied flow, and this is obtained in this. So the rate of change of that is slope of the water level is equal to s naught minus sf divided by 1 minus q square t by ga cube, and this q square t by ga cube is nothing but the square of the Froude number. So it is s naught minus sf divided by 1 minus fr square. Now if we consider a rectangular channel, in a rectangular channel the hydraulic radius is y, r is equal to a by p, and a by p will be approximately equals to y for a wide rectangular channel. And so we can get the discharge by Manning's formula, that is q is equal to 1 by n a r to the power 2 by 3 s naught to the power half. And yeah, so based on so we can get the friction slope as well as the where yn is the depth corresponding to uniform flow. So if we consider uniform flow, we can get the depth as y1, and based on that the q is obtained as this formula. And secondly, for the normal without considering uniform flow, we can get the discharge as this formula, that is simply taking y instead of yn. So if we take the ratio of the two formulas and we can consider discharge to be same, then sf by s naught will come as yn by y to the power 10 by 3. So if we substitute this formula in the dynamic equation, we will get this final formula, that dy by dx is s naught into 1 minus yn by y to the power 10 by 3, 1 minus yc by y to the power 3. So this is the basic equation that we will be using to get the different slope types and different types of gradually varied flow. So let us see through that. And yeah, one more thing, when we analyze for different slopes types and different types of surface profile of gradually varied flow, there are two main assumptions. One is q, n and s naught are fixed, that is discharge, the roughness coefficient and the bed slope are fixed. And secondly, yn and yc are fixed. So it is yc is the critical depth. critical depth and the normal depth. So normal depth is corresponding to uniform flow and critical depth corresponds to critical flow. So these two values are also fixed. So based on the dependence of the relation between y and normal depth and critical depth, we can classify the slopes into 5 types. The first type is the critical slope. The critical slope is when S naught equal to SC, that is normal depth is equal to critical depth. Secondly is mild slope, when yn, this normal depth is greater than critical depth and bed slope is less than critical slope. Thirdly, we have the steep slope. Here S naught is greater than SC, that is bed slope is greater than critical slope and a normal depth is less than critical depth. So these are 3 main slopes that we will be analyzing, but there are 2 other slopes, and the one is horizontal slope, when the S naught is equal to 0. In that case the normal depth will be infinity. And lastly we have the adverse slope, where S naught is less than 0, that is the bed slope is increasing along the downstream. In that case the normal depth will be imaginary. So these are the slope types, and for this these slope types we will be seeing what are the surface profile of the flow. So the first one we saw that when yn is if we consider the mild slope, that is S naught is less than SC, in that case this is yn and it is yc. Yn is greater than yc. Steep slope, again we discussed here, yn is less than yc. Critical slope, yn equals to yc, and the horizontal slope, yn tends to infinity, and lastly is the adverse slope, where yn is imaginary. Now suppose if we consider the case of first case, that is mild slope. So we know yn and we know yc. So the depth of flow, that is y, it at any instant of time can be in 3 regions, that is it can be greater than yn, so if it falls in region 1, or it can be between yn and yc, it can fall in region 2, or it can be less than yc, that is it can fall in region 3. So based on the 3 conditions we will get 3 surface profiles, and these surface profiles are called the M curves. That is for mild slope we call it the M curves, for steep slope we call it the S curves, and for critical slope we call it the C curves. Okay, so for we will see through for mild slope how the surface profiles are derived, like we'll get a basic intuition on that. So just see through this. So this is for mild slope. So the first one is M1. M1 is when y is greater than yn and greater than yc. Y naught, that is it is in the region 1. So this region is corresponds to M1. Secondly, M2 is when yn greater than y greater than yc. So this region, the flow in this region is corresponds to M2, and the flow in the zone 3 is corresponds to M3. So let us see through the regions one by one. If we consider the flow in zone 3, that is at the when y is less than both y2 and yn in this region. So if we consider that region, so y is less than yc and less than yn, so dy by dx will be greater than 0. Why? We'll see, get to know from this formula. Here y is, for M3 condition, if we see y is less than yc less than yn. So in this case, so y is both less than yc as well as less than yn. So this term will be greater than 1 since, and this term also be greater than 1. So both these terms will be negative, and negative by negative will be positive, so dy by dx will be greater than 0. So dy by dx is greater than 0. Now as y tends to yc, what will happen? As y tends to yc, so if this tends to yc, then this whole term will tend to 1. So 1 minus 1 will tend to infinity. So 1 minus 1 will tend to 0, and this whole term will tend to infinity. So it won't tend to infinity, it will be tending to minus infinity. And as y tends to as y tends to 0, that is y is just at the bottom slope, just near the bottom slope. In that case, what will happen? Dy by dx, if y is 0, so if we take y is equal to 0, 1 minus 0, 1 by 0 will be infinity, so this will be minus infinity by infinity, so minus infinity by minus infinity, so it will be infinity. So dy by dx will be infinity. So we can see this is the type of profile in M slope. As it reaches yc, this is yc, we can see the slope will be tending to infinity, that is slope will be tending to infinity, so angle will be approximately 90 degree, and at y equal to 0 it will also tend to 90 degree. So this is the M3 profile. Similarly, next we will see for zone 1. Zone 1 is when y is greater than yn and greater than yc. So in this case, first let us see the upstream condition. Upstream is when y tends to yn. Sorry, this is not no, this is I think this is from Miles loop. This is M3. Okay. So upstream part we will see that when y tends to yn, in this, that is in upstream part y tends to yn. When y tends to yn, what will happen? So if y tends to yn, so yn by yn is almost approximately 1, and 1 minus 1 will go approximately to 0. So dy by dx will go to 0. So dy by dx will go to 0 means the slope will be parallel to the normal depth, that is normal normal depth line. Now as we go downstream, then y will be greater than yn. So when y is greater than yn, what will happen? Again, when y is greater than yn, so this part will be less than 1, and this part will also be less than 1. So this is greater than 0, this is also greater than 0, so this whole part will be greater than 0. So dy by dx will be positive. And okay, dy by dx will be positive. And as we proceed, suppose when y is tends to infinity, that is y is extremely greater than yn, in that case yn by y will tend to 0, and also c by y will also tend to 0. So dy by dx will tend to s0, so that curve will approximately go to the slope s0 and downstream. So when the slope tends to s0, this means that the flow will be parallel to the ground slope. And the third case is in the zone 2, when y is between yn and yc. In that case, that bottom part, that is the numerator, is 1 minus yn by y to the power 10 by 3. So yn by y will be greater than 1. So 1 minus of greater than 1, that part will be less than 0. and denominator where y is greater than yc. In that case, the denominator yc by y will be less than 1, and 1 minus yc by y to the power 10 by 3 will be greater than 0. So numerator is less than 0 and denominator is greater than 0, so dy by dx will be negative. So in the upstream section, when y tends to yn, in that case, if we have seen that when y tends to yn, the numerator will tend to 0, so dy by dx will tend to 0. So the flow will be approximately horizontal in the upstream part. And as we move to the downstream part, when y will tend to yc, in that case the denominator will be yc by y will tend to 1, so 1 minus approximately 1 minus 1 will tend to 0, so the whole term will tend to minus infinity. So dy by dx will tend to minus infinity, so approximately perpendicular to y, the critical slope. So this is the M2 profile. So this is how we can see through the surface profiles, that is M1, M2, M3. Similarly, we can see how the profiles will be varying for steep slope also, where just the difference is that in steep slope the slope, just the normal depth will be less than critical depth. Now we'll see just the basic overview on the critical slope and the adverse slope. What happens in a critical slope? Now in a critical slope, we have seen that yn is equal to yc. In that case, only there will be two zones, that is zone 1 and zone 3. There will be no zone 2 since yn is equal to yc. So we will get two curves, that is C1 and C3. So in the first zone, that is when y is greater than yc. So this is the critical slope. Yeah. When y is greater than yc, this is condition 1. So in that case, dy by dx will be positive as y is greater than yc, so yc by y will be less than 1. So in that case, both denominator and numerator will be greater than 0, so term will be positive, and as y tends to yc, dy by dx will tend to s0, because yc by y s0, and as y tends to yc, dy by dx will tends to s0, and when as y tends to infinity, that is in downstream, when the depth of the water is very high than a critical depth, in that case the dy by dx will approximately equal to 0. So horizontal line. And in the second case, the third case, we don't have a second case here, so we'll only have a third case when y is less than yc. In that case, also dy by dx will be positive, since both denominator and numerator will be less than 0. So the total term will be positive, and as y tends to yc, dy by dx will tend to s0. And similarly, as y tends to 0, dy by dx will also tend to s0. So the C3 curve will be more or less a horizontal line, since both upstream and downstream the slope is approximately equal to the ground, that is slope of the bed slope. And lastly, we have the adverse slope. In adverse slope, the thing is that the depth of the bed slope is increasing along the downstream direction. In that case, there will also be only two zones. So when first case is when y is greater than yc, this will indicate dy by dx is negative, and as y tends to yc, dy by dx will tend to minus infinity, and when y tends to infinity, dy by dx will tend to s0. So this is the adverse slope. So one thing is when in the here, when y tends to infinity, you have to say dy by dx will tends to s0, and when y tends to yc, that is at this point, with dy by dx will tends to minus infinity, so it will be approximately perpendicular. And third zone, this is a3, this is a2, the third zone when y is less than yc, so depth of flow is less than the critical slope. In that case, dy by dx will be positive, and as y tends to yc, dy by dx will tend to minus infinity, and y tends to 0, dy by dx will tend to infinity. Okay, this was about discussion about the slopes, and just we'll see how these slopes can be obtained. So the first case is m1 slope. M1 slope, it occurs at the back end of a reservoir. So oblique dam. So if we consider this as a dam, then if the water is coming like this, so this is called, this will form the reservoir, and in the reservoir the surface profile will approximately be m1. This is how we get m1 profile. Now we can get m2 profile when the slope is varying simply like that, and we don't have any obstruction in between, and there is a sudden end of the slope. In that case, we will get the m2 slope. And we have seen third is the m3. M3 is when y is less than critical depth, and we have seen in previous class that when y depth of the flow is less than critical depth, we call it a supercritical flow. And a supercritical flow can be obtained when on the downstream of a sluice gate. So if we have a sluice gate, it is this is a reservoir end, this is a sluice gate, and if we open the sluice gate from bottom, so there will be supercritical flow. So depth of the flow will be increasing along the length, and this will give the m3 profile. It is along downstream of a sluice gate. So these three same cases can be obtained for steep. This is for the mild slope. If we have the slope as a steep slope, then we will get, instead of m1 we will get s1, instead of s2 we will get m2 will get s2, and instead of m3 we will get s3. So this will depend on the bed slope. If the bed slope is steep, we will get the s profiles. If the bed slope is mild, we will get the m profiles. So this was about gradually varied flow. I hope there are no doubts. If there are any doubts, you can ask me. Okay, so if there are no doubts, we will proceed. So next we will see rapidly varied flow. So rapidly varied flow is a unsteady non-uniform flow, and there are two types of rapidly varied flow. One is called the hydraulic jump, and the other is called the surge. So first, let us see the hydraulic jump. A hydraulic jump is formed when the flow changes from supercritical to subcritical in a very small instant of time and over a small distance. So the assumptions in hydraulic jump are that initially, that is in the upstream and in the downstream section, the flow is uniform. There is no rapid change of flow in the upstream and downstream sections, and the friction losses in the hydraulic jump are extremely small, or it can be neglected since the hydraulic jump occurs over a very small distance. And thirdly, the channel flow will be considered as horizontal. So this is how hydraulic jump. So initially it is in supercritical depth. The depth of water in the downstream is subcritical, and the flow changes from supercritical or subcritical over a small distance, and there are a lot of eddies formed that will lead to discharge of energy. Sorry, dissipation of energy. So in a hydraulic jump, what is conserved? So we cannot conserve energy in case of hydraulic jump, since we have already seen that there will be a huge loss of energy in a hydraulic jump. So in the hydraulic jump, so we will be conserving the specific force. So it is also equivalent to conserving the momentum. So the specific force is given by this formula, where F is equal to Q square by Ga plus A into Z bar. Z bar is the depth of the mean depth of the flow. And also one more assumption is that the pressure distribution is hydrostatic. So if we conserve the specific force before and after the hydraulic jump, and substituting the values of Z1, Z2, we will get the relation between the sequent depths, that is depth before the flow, that is y1, and a depth after the depth before the hydraulic jump, that is y1, and a depth after the hydraulic jump, that is y2. So y2 by y1 we can get by this formula, my half of minus 1 plus under 1 plus 8 FRN square, and similarly y1 by y2 half minus 1 plus under 1 plus 8 FR2 square. And the loss of energy, in the hydraulic jump can be obtained as V1 minus V2 whole cube into 2G into V1 plus V2, or also it can be obtained by this formula also, y2 minus y1 whole cube by 4 y1 y2. Okay, so these are very important formulas for entrance examinations also, and also for your course. So the height of the jump is obtained as y2 minus y1, that is here the depth, difference of depths, and the length of the jump is generally 5 to 7 times of the height of the jump. This is empirical. Okay, so there are 5 types of hydraulic jump. We will see the types of hydraulic jump. First is, so the type of hydraulic jump will be based on the Froude number, that is upstream Froude number that we got, FR1. So first one is the undular jump. So this occurs when the Froude number is in the range of 1 to 1.7. Second is the oscillating weak jump. So very small amount of energy is dissipated in weak jump, and this is when Froude number is in the range of 1.7 to 2.5. Third is the oscillating jump. So in that case, the jet of water in the hydraulic jump will be oscillating back and forth. This occurs when the Froude number is in a range of 2.5 to 4.5. The fourth one is a steady jump. This occurs when the Froude number is a range of 4.5 to 9. In that case, the hydraulic jump won't be moving to and fro, and it will be changing steadily from the position of the jump will be steady, and it will and there will be a high loss of energy. And last is a strong jump when Froude number is greater than 9. In that case, there will be a huge amount of eddies will be formed, and there will be a large dissipation of energy. So that was all about hydraulic jump. Now the second type of rapidly varied flow is surges. So what are surges basically? So surges are moving hydraulic jumps. When a hydraulic jump is moving in the flow, in that case we call it a surge. And the surge can change the depth of the flow. So based on the how a surge is changing the depth of the flow, we call it a positive surge or a negative surge. A positive surge is when it is increasing the depth of the flow in downstream, and a negative surge is a negative surge will decrease the depth of the flow downstream. So there are 4 types of surges. So first one is type A positive surge. So in this type of positive surge, the surge will be increasing, the surge will be moving downstream and will increase the depth of the flow in downstream. So the velocity of the surge, that is Vw, will be given as, the absolute velocity of the surge will be given as c plus v1, where c is the celerity of the surge. And this type of surge is obtained when a sluice gate is suddenly opened in the upstream direction. A gate. Now, second type of positive surge is when gate is suddenly closed in downstream direction. In this case, suppose there is a gate here, a gate is suddenly closed. In that case, a surge will be moving in the opposite direction of the flow, and it will increase the depth of the flow in the upstream section. So this is a type B positive surge. Now the third is a negative surge, so type C negative surge. So this will happen when a gate at the head of the channel is suddenly closed. So if there is a gate here, a gate is suddenly closed, then depth of the flow will be decreasing here, and it also decrease the depth of the flow in the upstream direction. So the surge will be moving along the direction of the flow. And the last one is the negative surge, when the gate at the tail section, so if a gate is suddenly opened in the downstream section, when the gate is suddenly open, the flow will be flowing fast in this direction. So in that case, there will be decrease of depth in the backwater, and this will create a negative surge moving upstream, and this will decrease the depth of the flow in the upstream direction. So this is also a negative surge. The type D negative surge, when the gate at the tail end of a reservoir, tail end of a sluice is suddenly opened. We'll just see through the basic conservation laws that can be used to obtain the velocity of surges. So the first one is the type A positive surge. In type A positive surge, what we have seen, that when the gate, due to sudden increase of flow, when the gate is suddenly opened in the upstream direction, gate is suddenly open, so the flow will increase, it will move a surge in the downstream direction. So here Vw is the velocity of the surge, V1 and V2 are upstream and downstream velocities, and Y1 and Y2 are depths at Y1 section 1 and section 2. Okay, sorry. Okay. So considering, so we have seen that when a surge is moving on top of the mean velocities, so this will create a unsteady flow. So in order to do the analysis, first we have to convert the flow to a steady flow. So how will we do that? We can make if we can take the velocity of the surge relative to the mean velocity, that is, we consider a moving reference frame, that is moving at the velocity of the surge. In that case, what will be the velocity of the flow upstream, flow downstream. So downstream flow, so this is downstream and this is upstream. So downstream flow will be V1 minus of Vw, since the observer or the reference frame is also moving in the same direction of the flow with a velocity of Vw. So since it is moving in the same direction, so the relative velocity will be V1 minus Vw. Similarly, for the upstream section, it will be V2 minus Vw. Now we have obtained a steady reference frame. So after getting that, we can use the continuity equation. So the continuity equation will say that is A1 V1 equal to A2 V2. So in case you take the breadth, that is the breadth of the channel as same, so we'll get Y2 into V2 plus Vw into Y1 equal to Y1 into V1 minus Vw. So Vw can be obtained as V1 Y1 plus minus V2 Y2 by Y1 minus Y2. and from the this is the momentum equation, and by solving the momentum equation we can get the velocity of the surge as this formula under g y2 by 2 y1 plus y2 plus v1, and this whole term is called the c. C means the celerity of the wave, that is surge wave. And yeah, so one special condition is when the depth of the flow, that is height of the surge is extremely small. This is h is the height of the surge is extremely small compared to the total depth of the flow. In that case, the celerity of the surge is given as under root of g y1. So this is for type A positive surge. Then there is a type B positive surge. The type B positive surge is when the downstream gate is suddenly closed, so there will be increase in flow in this backwaters, and our surge will be moving in the direction opposite to the flow. So in order, if we take a reference frame moving with the surge opposite to the direction of flow, so in that case if we get the relative velocity as v1 plus vw, here it will be v1 plus vw, and here it will be v2 plus vw. So we obtain two velocities, and now we can use the similarly we can get the continuity and the momentum equation, and we'll get the velocity of the surge. So and the second case is when the gate is completely closed, not partially closed. When the gate is completely closed, in that case the v2 will be 0 since the gate is completely closed. So the equation, continuity equation, will be just replace v2 velocity of that v2 by 0, and rest everything is same. So this is a type A and type B positive surge. And the third is the negative surge. A negative surge is generally very temporary. It won't be lasting too much in time, since it has to be a since the change in energy is not that much, so it is sustain. It cannot sustain for a long amount of time. So a negative surge, the velocity of a negative surge is obtained as c minus v, where c we have seen root gy. Here it is root gy minus v, and the velocity of the crest of the wave. So this, if we take this as the crest and this is the trough, so the crest will be root g y2 minus v2. So if we take this as y2, so the velocity of the crest of the surge wave will be root g y2 minus v2, and the velocity of the trough of the wave will be root g y1 minus v1. So the mean velocity of the surge will be root vw1 plus vw2 by 2. So this is just for a negative surge. Okay. So we have seen through the concepts, basic concepts that are involved here. So we will be solving one or few questions related to the concepts that we obtained. Okay. So the first question: if the value of rate of change of specific energy is 7 into 10 to the power of minus 4 and s f equal to 0.0013, calculate the value of Petz's law. So we have seen before that the dE by dx, I think we have seen the formula for this is the formula for dE by dx. So dE by dx equals to dy by dx into 1 minus q square t by g aq. And if we substitute the value of dy by dx, it will be s naught minus sf g aq. So these terms will be cancelled, so it will be s naught minus sf. So now just substitute the values. So d by dx equal to 7.03 into 10 to the power of minus 4. S naught you have to find out, and sf is 0.0013. So if we calculate, it will be at s naught will come around 1 by 1200. So second question is, which of the following assumptions about a gradually varied flow is false? The channel is prismatic. Yes, the channel can be prismatic. There is this is a true assumption. The pressure distribution hydrostatic. Yes, we consider pressure distribution hydrostatic. Flow characteristic change with time. No, this is false. The main definition of the gradually varied flow is that it is steady non-uniform flow. Steady. So if it is steady, then dv by dt, d of x by dt or v by dt will be 0. So it won't change with time. And the roughness coefficient is constant. Yes, that is also true. So the third question. A long prismatic channel ends in an abrupt drop in bed. Which of the following statements explains the water surface profile on the upstream of the drop of an initially subcritical flow? So what do you think? A long prismatic channel ends in an abrupt drop in bed. So if this is the initial bed, so there is a abrupt drop in bed. If the initial flow is subcritical, if this is yc, then y is greater than yc. So if the initial flow is subcritical, then which of the following statements explain the surface profile? Since the initial depth is subcritical, that is around, we can consider the flow to be slope to be m2 slope, and if we consider m2 slope, that is greater than yc for mild slope, and the flow profile due to the introduction of a sudden drop is m2, and the m2 profile between NDL and the normal depth line and the critical depth line, and joining the normal depth to the downstream and asymptotically is, it can be seen. Okay, so we have seen this case. Yeah, this is the m2. So initially flow is subcritical, there is a sudden drop in the bed, and in the upstream direction it will be joining the normal depth line here NDL, and in the upstream there will be sudden, the flow will be almost perpendicular to the critical depth line. So the this is yn. if it is considered as a yn, initially it is asymptotic to yn, and after some time it will be falling like this. So this is the M2 profile. The correct answer is water surface profile lies between critical depth and joins the normal depth line asymptotically in the upstream direction. M1 would have formed if we have placed the reservoir here or a blockage, then we could have got a M1 profile. But in this case, in the sudden drop, there is no blockage under the tail section, so it will be a M2 profile only. Now coming to the next question. The flow in a rectangular channel is subcritical. If the width of the channel is reduced at certain section, the water surface under no choke condition will be okay. I have discussed in the previous week lecture, if the width is suddenly constricted, okay, this is B1, B2, the discharge will be Q1 and Q2 will be same. If the width of the channel is reduced a certain section, the water surface under no choke condition, that is there is the water level won't be changing from subcritical to supercritical. So first we have considered that the flow is subcritical, so it will be somewhere here, and E1 is equals to E2. Since the beds, there is no change in the bed slope, so we know that E and the datum is not changing, so E1 it will be equal to E2. So this is Y versus E diagram. So if we take this as E1, then this is E2, E1, this is E2, and E2, why can't E2 be here? E2 cannot be here because it is clearly given it is a no choke condition. No choke means the surface profile is not changing from subcritical to supercritical, and so it should be remaining in the subcritical region. So if it has to remain a subcritical region, then E1 and we have seen from the basic from the concept of specific energy that E1 and E2 will be same, since the datum is not changing. So the what will happen to Y? So initially if it is Y1, after reduction of depth, after reduction of weight, the surface profile will be reducing to Y, will be given by Y2, and Y2 is less than Y1, so there will be a drop in the depth of the flow, so drop at the downstream section. I hope this is clear. If there are any doubts, don't hesitate to ask me anyways. Okay, next question. In a hydraulic jump occurring in a horizontal rectangular channel, the sequence depths are 0.45 meter and 1.8 meter. So Y1 is 0.45 meter, Y2 is 1.8 meter. So we need to get the energy loss in the jump. So delta E is given by Y1 minus Y2 whole cube by 4 Y1 Y2. So if we just substitute the values here, sorry, this is Y2 minus Y1, 1.8 minus 0.45 whole cube, 4 into 0.45 into 1.8, so this will give 0.759 meter. Okay, what is the next question? The sequent depth ratio of a hydraulic jump in a rectangular channel is 20, that is y2 by y1 is equal to 20. The Froude number at the beginning of the jump, that is we have to need FR1. So how will we obtain FR1? We can directly use the formula of y2 plus y1. This is given as half of minus 1 plus under 1 plus 8 FR1 square. This will give 20. So there is, now we have to solve it. So it is 2 into 40, 40 plus 1, 41. So if we solve, I think FR1 will come approximately, I think 14.5. These are very simple questions. When the hydraulic jump is in a moving form, it is called a positive surge. We have seen that. Okay, these are some basic questions. So I have taken some questions. We will be solving some numerical questions now. Okay, so first question is, let us go to what is given in the question. The water flows from under a sluice into a very wide rectangular channel. The channel has a bed slope of 1:1000. The sluice is regulated to discharge of 6 meter cube per second per meter width of channel. The depth at the vena contracta being 0.5 meter. Will a hydraulic jump form? If so, determine its location, and using a single step for the computation using Manning's n equal to 0.015. First, let us see how the flow is taking place. If this is a flow, this is suppose upstream depth. So the water is flowing from under a sluice gate. This is a sluice gate. And we are suppose it is asked if a hydraulic jump will be forming. Okay, we'll see. So if a water is flowing in this fashion, suppose we first let us assume that a hydraulic jump will be forming and in the downstream, and finally a depth y2 is obtained here, suppose y2 or something, and this is the vena contracta region. And the water depth given here is 0.5 meter, and the vena contracta is 0.5 meter. And if we take bed slope, S naught equals to 1 by 1000. So bed slope is given as 1 by 1000. The sluice is regulated so that to get a discharge of 6 meter cube per second. Okay, so now it is go through the read the question carefully. So first, it is given a very wide rectangular section. In what do you know for a wide rectangular section? In a wide rectangular section, what happens? The hydraulic radius, it is A by P. If we consider By by V plus 2y, this 2y, y is less than B. So the B plus 2y can be replaced by B, and it is given as y. So hydraulic radius is approximately equal to the depth of the flow. So yeah, so if we let us obtain the normal depth of the flow, that is, if we consider uniform flow in the downstream section, considering uniform flow. Okay, if we consider uniform flow, what is the depth of uniform flow in the downstream section? How can we obtain? We can get that by Manning's formula. V is equals to 1 by n r to the power 2 by 3 s naught to the power of half. Now V is given by q by y 1 by n r to the power 2 by 3 s naught to the power of half. So q is 6 and y is yn here. Yn can be assumed. Okay, we have to find yn. 1 by n is roughness coefficient is given as 0.015. R is equal to yn. We have seen R is equal to y. And S naught is 1 by 1000 to the power of half. So if we solve this, we will get yn is equals to 1.873. I am not going to the numerical calculations, you can do that. I am just showing how to approach this problem. So we have obtained yn is approximately 1.873 meter. Now let us see the critical depth. So critical depth is given as q square by g to the power of 1 by 3. So q is 6, so q square will be 36, g is 9.81 to the power of 1 by 3, and this will come around 1.54 meter. Now yc is 1.54, and what we have seen that y1 is 0.5, so y1 is less than yc, and yn is greater than yc, y1 is less than yc. So first we have seen that yn is greater than yc. So what is the slope of type? The slope is mild slope. So this is a mild slope, and since y1 is less than yc, the flow will turn from subcritical to supercritical in a downstream, supercritical to subcritical in a downstream section. So their hydraulic jump will be forming. So where will the so the question is, what is asked? You have to find if a hydraulic jump will form, determine its location, at what distance will it form. Okay, so it will form, the jump will be located at a section where the depth of the flow will be conjugate to the normal depth of the flow. So jump will form where depth of the conjugate to normal depth. Now normal depth. So initially it was seen that y1 is 0.5. So after proceeding for some time, the value of y will be increasing. So this y should be a sequent depth or a conjugate depth of yn. So if this y is a sequent depth of yn, in that case the hydraulic jump will be forming at this section. So we have to find what is the distance between these two parts, that is y1 and y. Get the distance. Okay, so first of all, to get the distance, we first need to find what is y. So how can we find y? So we can find it by the formula for the ratio of sequence depths. The sequence depths, it is what is given, y1 by yn is equal to half minus 1 plus under root 1 plus 8 q square by g yn square. Okay, so this formula we have seen before. Yeah, this is the formula. Half of minus 1 plus under root 1 plus 8 q square by g y1 cube. a1 cube. So just substitute the values. y1 by 1.873 half minus 1 plus under root 1 plus 8 into 6 square by 9.81 into 1.87 whole cube. So if we solve this numerical, you will get y1 is equal to 1.253 meter. Now we have got the sequence depth y1 or y, let's give it y0 as 1.253 meter. Now we need to find the distance between y1 and y0. How can we get that? We can get by using the specific energy formulas. First, let us get us E1 at 0.5 meter. So E1 will be equal to 0.5 plus v square by 2g, where 6 by 0.5 whole square by 2g, and this will come around 7.83 meter. Next we get E2, E0 will be at 1.253 meter. Three plus 6 by 1.253 whole square by 2 into g, and this will come around, I think, 2.42 meter. Now delta E is equal to, if we subtract 1 minus 2, it will be around minus 5.417 meter. So now we obtained one formula that dE by dx equal to S0 minus SF. We know S0. If we can get SF, then we can get the change. We know dE, then we can obtain dx. So that is the change in distance. So how do we obtain SF? SF will be the average of the friction slope at y1 at SF1 plus SF0 by 2. Average of the friction slope at the depths y1 and y2. So first let us get SF1. SF1 will be given as v square into n square by r to the power 2 by 3. This is from Manning. This is from Manning's formula, and if we substitute, it will get 8.16 into 10 to the power of minus 2, and SF0 we can get similarly by v square n square by 3 at 1.25, and this is at 0.5. This will come around 0.38 into 10 to the power of minus 2. So the average friction slope will be the average of these two values, and it will come around 4.27 into 10 to the power of minus 2. So we have obtained SF, we know S0, so let us get X. So delta x equal to delta E by S naught minus SF. So delta E is minus 5.417, S naught is 0.1 into 10 to the power of minus 2 minus of 4.27 into 10 to the power of minus 2. So just solve and you will get I think around 130 meter. So at a distance of 130 meter from the sluice gate we will get a hydraulic jump. I hope this is clear. If there are any doubts in this question, you can ask me. Okay, then if there are no doubts, I will proceed to the next question. Okay, so yeah, what is given in this question? The depth and velocity of flow in a rectangular channel are 0.9 meter and 1.5 meter per second. Y is given as 0.9 meter, V is 1.5 meter per second. If the gate at a downstream end of the channel is abruptly closed, what will be the height and absolute velocity of the resulting surge? And if channel is 900 meter long, how much time will be required for the surge to reach the upstream end of the channel? So this is a type B surge that we have seen. Okay, let's have a just see the diagram. Okay. Just copy this diagram here. Okay, initially what is given? V1 is given. V1 is 1.5 meter per second. Downstream gate is completely closed, so V2 will be 0. It's completely closed, it is given. So what will be the height and velocity of the surge? So we have to obtain HW and VW. So let us go write the first equation, that is the continuity equation after assuming a steady, that is after assuming a moving reference frame. So y1 into v1 plus vw equals to y2 into vw. So we know y1 is given as 0.9 and v1 is 1.5 plus vw is equal to y2 into vw. We still don't know y2, so for getting y2 we will have to write the momentum equation. So if you write the momentum equation, what will you get? Momentum equation gives half of y2 squared minus y1 squared. We've seen the equation before, and directly writing the equation here, I won't be deriving it here, I have already derived it before. So it is y2 by g into vw into v1. So I can substitute the values, half of y2 square minus of 0.9 square equal to y2 by 9.81 into vw into 1.5. So if we substitute VW from 1 in 2, if we substitute VW, so to get VW, what will you get? VW is equals to 0.9 into 1.5 divided by y2 minus 0.9. So 1.35 divided by y2 minus 0.9. So if you substitute VW here in 2, what will you get? Half of y2 square minus 0.9 square. W will be 1.35 divided by, so we'll get a cubic equation. So if we rearrange the terms, we'll get the equation as y2 cube minus 0.9 y2 square minus 1.223 y2 plus 0.72. So you cannot directly solve a cubic equation, so we have to solve it by trial and error. So we have to first assume some values. Suppose if we assume a value of 1, we'll see how close it is to 0. Then we will see how we put a value of 2, we'll see how close it is to 0. And if we, and based on that, we'll assume a value somewhere between 1 and 2, and by proceeding in this trial and error method, or you can directly solve this cubic equation using a scientific calculator. If we put the equation, then the scientific calculator will give a approximate value. So by solving by trial and error, we will get y2 is approximately 1.401 meter. So we got y2. So what will be the VW? The velocity of the surge will be 1.35 divided by 1.401 minus 0.9. So this will be approximately 2.69 meter per second. And the time required for the surge to reach the upstream end, what will be time required? The distance is given as 900 meter, velocity is 2.69. So distance by velocity is equal to 5 point, will be approximately 334 seconds. Okay. I hope if there are any doubts, you can still ask me, else I will proceed to the next question. So one final question we will be solving. Okay then. Okay, so last question. What is given in this question? A trapezoidal channel having bottom width of 8 meter and a side slope of 1:1 carries a discharge of 80 meter cube per second. Find the depth conjugate to initial depth of 0.75 meter before the jump. Also determine the loss of energy in the jump. Okay. So it is given a trapezoidal channel, bottom width is 8 meter and this is 1:1. The slope is 1:1. Okay, so whatever will be the depth of the flow, so what will be the depth of flow, these two values will be identical. Okay, let's see So initial depth is given as 0.75 meter. So this will also be 0.75, and this will also be 0.75. So let us get the area and the centroid of the, that is the mean depth of the flow. So the thing is that for using to get the conjugate depth, we will have to use the conservation of specific force. For a rectangular channel it is straightforward, but since it is trapezoidal channel, we have to derive the formula for the specific force and then get the conjugate depth. So let us first get in the initial section. So in that case, that is when y1 is equal to 0.75 meter. So let us get a1. What will be a1? a1 will be b plus b plus so the area of a trapezoid is given as half into distance between parallel sides into sum of parallel sides. So it will be half into sum of parallel sides will be, so b plus 2 into 0.75 into depth of 0.75. So it will be half of 2 into b plus 0.75 into 0.75. So half and 2 will get cancelled. So a1 will be 6.56 meter square. Okay, now z1, but that is the mean depth of the flow. So this is given by the formula y1 by 6 3b plus 2 z y1 divided by b plus z y1. So it will be 0.75 into 24 plus 1.5 divided by 6 into 8 plus 1.8 plus 0.75. So this will give 0.364 meter. Now similarly at conjugate depth after jump, we will get a2 is equals to 8 plus y2 into y2 by similar formula, and similarly z2 bar is equal to by 6 into 24 plus 2y2 based on the similar formula. So now conservation of specific force. So if we conserve specific force, how is the formula given? It is q squared by I'll show the formula once. So q square by ga1 plus a1 z1 bar, q square by ga2 plus a2 into z2 bar. into q square by ga1 plus a1 z1 bar q square by ga2 plus a2 into z2 bar. So we have q is given, I think, discharge of 80 meter cube per second. So let us substitute the values. 80 square by 9.81, a1 is given as 6.56 we obtained, plus 6.56 into 0.36 we obtained z2 or z1. Similarly now q square is 80 square plus g into g is 9.81 into what is a2. a2 is 8 plus y2 into y2 and plus what is a2 into z2 will get y2 square by 6 into 24 plus 2 y2. Now this will give a fourth order polynomial, and the fourth order, if we solve all the fourth order polynomial by scientific calculator, then we will get y2 is equal to 4.06 meter. So this is the depth after the hydraulic jump. So the loss of energy in the jump will be given as difference of specific energy. So what is different? How do you obtain that? So if E1 is equal to Y1 plus V1 square by 2G, so this will be 0.75 plus 80 square by 2 into 9.81 into 6.5 whole square, and E2 is equal to Y2 plus V2 square by 2G. So this is 4.06 plus 80 square by 2. So this is equal to around 8.33. This is equal to 4.2 meter, and delta loss of energy is equals to E1 minus E2. This is approximately 4.13 meter. Okay. So this is just numerical. The thing is that for solving this kind of polynomial equation, you will have to anyways have to use scientific calculator. You cannot do it by hand. So this is the main challenge in solving these equations for specific force, or the cases for hydraulic jump. Okay, we will see through one final question. This is similar to the first question. So in a horizontal rectangular channel, 3 meter wide and 2 meter water depth, conveys water at 18 meter cube per second. If the flow rate is reduced to 2/3 of original value, compute the magnitude and speed of the upstream surge. So we have to obtain the speed of the upstream surge. Assume that the front of the surge is rectangular and the friction in the channel is neglected. This is a type A positive surge. That is, suddenly a gate is opened and a surge will be moving in the direction of the flow. So this is Y2 similar. So obtaining sorry, so this is not a type A, this is type B only. Sorry for a type B positive surge. Flow rate is reduced by closing the gate. Y2 V1 Y1 is VW, and the gate is not fully closed, it is closed such that the flow is reduced. V2 final is equals to 2/3 of original value. Two by three of V1. Okay, so we can get the continuity equation. The continuity equation is this: y1 into v1 plus vw into y2 into v2 plus vw. So we know y1, it is 2 meter, it is given, and v1 is 18 by, that is this is q by area, so q by 3 into 2, it is 3 meter cube, 3 meter per second. Now v2 is given as 2 by 3, 2/3 of v1, 2 by 3 into 18 by 3 into y2. So initial depth is y2, so it is reduced to 4 by y2. So now let us substitute these values in the continuity equation. We will get a relation between Vw and y2. Now Vw into y2 minus 2 is equal to 2. Now we will see the momentum equation. So this is the momentum equation. Substitute the values of Vw and get the equation in terms of y2. So we will get a fourth order equation here for y2, and if we solve for y2, we will get around 3.93 meter. So we got this. Now the height of the surge is equals to y2 minus of y1, and this will get the height of the surge, and the velocity is again similar. Here we have, this is the value, it is 2 by yw, y2 minus 2. It's similar to the first problem, where the only difference is that in the first problem of surge, we have seen that the gate is completely closed, but here the gate is not completely closed, it is kept closed partially, so that there is a reduction in the flow velocity. Okay, so I have discussed this some problems. So if there are any doubts, you can ask me. I will wait for some time, and if there are no doubts, we will close the session. Okay then, thanks for attending the session. If there are any doubts, you can just post in a discussion forum, or also you can ask in the next class. You can leave the meeting now. Thank you. session.